0.675. So 0.392 plus by 0.675 is equal to 1.067. Okay, inches cube. Okay, so now I'm going to have my shear stress at point C is equal to V over I or Vy over IZZ. QZ is 1.067. Divide by the thickness of 0.3, and I have to include 2 over here because there's 2Q. Okay, so 1.067 divided by 0.3 divided by 0.2 is equal to 1.067 divided by 0.3 divided by 2 is equal to 1.778. Okay, so 1.778 V over I. So what we realize that at point C, the shear stress at point C is greater than shear stress at point A and the shear stress at point B. And we don't need to check anymore. Why we don't need to check any other position? Because this is our Q what? Our Q max. So therefore, with this, we know that the shear stress at point C is equal to our max. Okay. Now, I'm going to do something, another way of doing this. Okay. And I'm going to just look at the bottom below the centroid. Okay. And the answer will be the same. But I think it's important that I show you that the answer is the same and not just tell you, oh, the answer is the same. Not like this. Okay. So what we have over here, okay, then I'm just going to cover the top now. So now this becomes a white flange because you have two different terminals now. So this is your terminal 3. This is your terminal 4. So now we are going to analyze so the analysis bottom of centroid. And now it is a white flange. And you have Q. Okay. So the Q at the centroid, we know up to here, right? I'm going to divide this differently up to here. And then we have to do the rest over here, right? So that value over there is equal to, oh, I missed it. The value at Q is equal to 0.196. Okay, so QZA is 0.196 plus the width over here is 0.3. The depth over here is 1.5. The Y bar is 1.5 divided by 2. Okay, so this will be equal to 0.3 times by 1.5 times 1.5 divided by 2 plus by 0.196 is equal to 0.196 plus by 0.3 times 1.5 times 1.5 divided by 2 is 0.5335, right, inches cube. Okay, so the shear stress at point C is equal to Vy over IZZ. Okay, the Y bar or the first moment of area, I do apologize, this is Q Z at point C. Okay, so it's equal to 0.5335, and then you just need to divide by the thickness of 0.3, and you don't need to put one because you only have a single Q. Okay, so 0.5335 divided by 0.3 So it's equal to 1.778 Vy over Izz. Okay, I should standardize Vy over Izz. So we realize that tau max, okay, whether you do from the top or from the bottom, the answer will be the same. You decide, okay, you decide which one, which you should. For this case, I don't think it makes a lot of difference, okay? I don't think it makes a lot of difference. Let me fill this up first, okay? So now, while knowing that Vy over Izz or at point C is a tau max, so we know that tau max is equal to 1.778 Vy over Izz, and this will be equal to the value of given to us 10 ksi, so 10 times 10 to the power 3. So therefore, Vy over Izz is equal to 10 to the power 3 divided by 1.778. Okay. So this will be equal to 10 power 3 divided by 1.778 is equal to 5.624, right, times 10 to the power 3. And the units down here is Newton per meter 4, right, because it's Vy over Izz. So therefore, we know that the shear stress at point A is equal to shear stress at point B, and is equal to Vy over Izz, and I think it's 0.98. Am I right? Yeah, 0.98. So this will be equal to 5.624 times 10 to the power 3 multiplied by 0.98. Okay, so 5.624 power 3 times 0.98 is equal to 5. I get 5.512. Oh, sorry, I got the units wrong. I'll come and correct it. 5.512 times 10 to the power 3 psi. Okay, so this is equal to pound over inch to the power of 4. Okay. So as I said, this is a very interesting problem. Okay. I find this interesting because initially when I taught this course, I find it like not easy to solve a problem like that. And why? Because this problem combine what? Okay, combine both wide flange and box beam. Okay, but you can see at the centroid, whether you use wide flange or box beam, the answer is the same. Okay, which it has to be. If not, mathematically, there is serious doubt. Okay, so this is our answer over here. Anyone have any question regarding this before I do a difficult example? Anyone? Okay, I don't hear anyone has a question. So as I said, this is a tough problem. It's not a basic problem because over here, because you have a structure that combine both wide flange and box beam, and to help you, you just draw the box like what the green box that I show you. It's so much clearer. If you just look at a structure like this, right, without covering it, you're like, what should I be applying? It's not so clear. Are we clear? That's why I make the rules what the why I can cover it, because remember one of the rules, this is our what, our centroid. The first moment of area cannot cross the centroid. That's the reason I set up that rule. Okay, then it's so much clearer. Okay, so what I propose is that we go for a 5 minutes break. Okay, I'm going to go off grid because my computer is so hot now, it's hopeless. And then I'll come back in 5 minutes time. I'll see all of you at 8:15. Okay.